Welcome to the IEEE MTT-S Historical Exhibit, presented at the International Microwave Symposium. Here, you can take a deep dive into the earliest vacuum tube prototypes, Klystrons, and solid-state devices, all of which laid the foundation for today's most cutting-edge RF and microwave-enabled devices. Let's celebrate the innovations of early RF and microwave pioneers. The first military application of vacuum tubes was in World War I. By the early 1920s, commercial broadcasting had begun. Experimenters used radio waves to detect ships and aircraft. Operating at higher frequencies with shorter wavelengths enabled ships and aircraft to use smaller antennas with sharper beams. By the mid-1930s, tubes were able to operate at frequencies of hundreds of megacycles per second, or megahertz. Tubes with shorter leads between the internal elements and the external circuitry were developed to reduce parasitic effects that limited their useful frequency range. Acorn and doorknob tubes, so-called because of their shapes, were useful up to a few hundred megahertz. Other tubes were developed using a planar design instead of the earlier cylindrical approach. This allows the tube to be more easily connected to high-frequency circuits. Some of these tubes are usable up to a few thousand megahertz or gigahertz. If the time it takes for electrons to travel from the hot cathode to the collecting anode approaches the duration of one cycle of the signal frequency, the tube will not be able to respond fast enough. In the microwave klystron, positive and negative voltages applied at the cathode cause electrons to speed up or slow down, forming bunches as the faster electrons catch up with the slower ones. When the bunches arrive at the anode, they produce an alternating current at an increased power level. If the output of an amplifier is fed back to the input, we can make an oscillator. In the early Klystrons, a sample of the output is fed back to the input through a cable, but it is also possible to provide feedback by reflecting the electrons back to the input inside the tube. A negatively charged electrode called the repeller or reflector provides this function. The tube is then called a reflex klystron and can be made to oscillate at tens of gigahertz. The frequency is controlled by a resonant cavity. These are all examples of reflex klystron oscillators. They were used primarily as local oscillators in super-heterodyne radar receivers. In some cases, the tube is mounted in an external cavity. In others, the resonator is built inside the tube. These klystrons are mainly from the 1950s. They were used as signal generators in test equipment or as transmitters in the microwave long-distance telephone towers dotted across the countryside. In a magnetron, the electron current is deflected by a magnetic field. This current is then passed through a resonant structure, producing an oscillating field. The magnetron can produce much higher power than the klystron, and so was used as the transmitter in most early radar systems. Several of these magnetrons are the split anode type, where the electrons oscillate back and forth between the two anode halves. The split anode type has a hairpin resonator that is internal to the envelope. The cavity resonator types use multiple resonators to produce very high power levels for pulse-type radar systems. The high-power split anode types were developed for continuous wave use in radar jammers. In a conventional radar, a transmitter produces a high-power pulse that is radiated by an antenna. A sensitive receiver detects reflections from any targets. The transmitted signal can be hundreds of kilowatts, while the received echo can be microwatts or less. If the transmitted signal were to reach the receiver directly, it would damage the receiver. TR tubes, or transmit-receive tubes, are designed to switch a single antenna between transmit and receive functions in a microsecond or less. These TR tubes are from the 1940s and early 1950s. A sealed chamber contains a gas that becomes ionized when exposed to the high transmitter power. The ionized gas reflects high-level signals away from the receiver. Weak received signals cannot ionize the gas and pass directly to the receiver. The traveling wave tube was developed shortly after World War II. A narrow beam of electrons passes along the center of the tube. A microwave signal travels in a slow wave transmission line that slows the RF to a speed that matches that of the electron beam. Energy is coupled from the DC current in the beam to the RF fields in the transmission line, resulting in gain. The amplification factor can be very large, and the traveling wave tube can operate over very wide bandwidth. Early traveling wave tubes used electromagnets to focus the electron beam. Modern designs use permanent magnets to reduce size and weight. Traveling wave tubes are one of the only types of vacuum tubes still used today in satellites. This is a collection of miscellaneous waveguide components spanning the range of development from the 1940s to the 1960s. The experimental waveguide monopulse circuit was made by lining a carved-out wooden mold with copper foil. These are solid-state devices used at microwave frequencies. The early microwave detector, at the top, used the heating effect of microwave energy to change the temperature and thus the resistance of the thin wire in a miniature fuse. The coaxial detector uses a crystal diode rectifier to produce a voltage proportional to the strength of an applied microwave signal. The bolometer detector uses the change in conductivity of a thin resistive film due to heating by an applied microwave signal. The two MIRA, or Molecular Electronics for Radar Applications modules, were used in the first solid-state phased array radar. Instead of mechanically scanning the antenna, a beam was formed by controlling the phase of individual elements in a large array. The solid-state noise source was used for laboratory measurements of receiver performance. The samples of waveguides are used to transmit microwave frequencies from 3 GHz, the largest, to 24 GHz, the smallest. Interestingly enough, the smaller waveguides can carry far more information than can the larger ones. In the lower left, this is an LHTR transmit-receive subassembly. It uses 2 lighthouse tubes in a transmit-receive arrangement. In World War II, it was widely used in low-power airborne tailgun radars. Although waveguide can handle high-power microwaves with very low loss, its size is a disadvantage. Coaxial transmission lines are much smaller and can be made to perform functions that would be difficult in waveguide. Some of these devices are true coax, having a concentric metal shield with a coaxially located center conductor. Other transmission lines use a narrow metal track between 2 flat ground planes, such as the early tri-plate construction. These are similar to the printed circuits commonly seen in low-frequency and digital applications. The early 1960s saw the beginning of microwave miniaturization. These are some of the tools, experimental pieces, and finished products developed in those early days of miniaturization. This is the prototype maser, microwave amplification by stimulated emission of radiation. It was used in the ground station for the 1963 Telstar satellite program. It was the first system to actively relay TV signals from space. This Ruby maser achieved a noise temperature of 3.5 Kelvin at 4 GHz. Thanks for joining us on this in-depth look at our microwave heritage. For more historical resources, visit MTT.org.